So today is, I love teaching this stuff. Today I'm kind of excited to teach you this. Today is a day where we get to look at something pretty cool. We're going to look at, for the first time in detail, at how the second derivative impacts the graph of a function. Okay, what does it tell us? You know, it does a couple things. It tells us concavity, which we're going to talk about today. That's a new term. It is associated with points of inflection, which are very important points mathematically for us, in the same way that extrema are valuable points for us. Inflection points are equally important. And it even gives us something called the second derivative test, which is, in certain situations, is a much easier and more efficient way to find extrema. Even though it's not directly associated with extrema, it provides us with an easier test than the first derivative test in some cases. Okay, and when it's easier, it's quite a bit easier. So, and we'll talk about that for the next few days that we're next few lectures. Okay, so moving on then. Let's just take a quick look at and kind of get our bearings here. What is the second derivative, and how do we come to grips with that? Right? We've hopefully at this point everybody's feeling pretty good about the relationship between the first derivative and the function, right? And let's just think about that for a second, right? What's the job of a function? A function takes an input x value and it outputs the y value if we're talking about a graph, right? It's giving us the value of the function is the value of the y coordinate if we're plotting the function in the xy plane, right? So the first derivative does something a little different, as you'll recall. We input an x value and it tells us the slope of the curve at that point. And the easiest way to think about that would be if we were to draw a tangent to the curve at that x value, it's telling us the slope of that tangent line, which is equivalent to the slope of the curve. When we say a slope of a curve in calculus, and I know we've talked about this, but the slope of the curve just means the slope of a tangent to the curve at that particular point. Okay, so the second derivative is a little harder to visualize. The further you get away from the function, the more counterintuitive it gets. The second derivative, by definition, is the rate of change of the first derivative with respect to x. Okay, so we can think about that as being the rate of change of the slope with respect to x. Okay, now think about what that would mean for an ant walking along the function. Right, slope makes sense. The slope is the rate of change of the function with respect to x. That's pretty easy to relate to, and our ants have those built-in slope sensors that give them a quantitative value for the slope as they're walking along the function. What would it mean for the ant if we had a positive or a negative second derivative? How would that manifest in terms of the topography that the ant is walking along, right? So if the second derivative is positive, think what that means. That means that the slope of the function is increasing with increasing x, right? Doesn't that mean that if the ant were walking on a part of the curve with a positive slope, if the second derivative were positive, then in order for the slope to be increasing, the ant would see increasingly steeper and steeper and steeper positive slopes as he moved in the positive x direction. Everybody get that? The slope would be getting steeper as he moved to the right. Okay? If he were walking on a downhill portion of his two-dimensional universe, right? If he were walking on a place where the slope were negative, but the second derivative were positive, well, if the slope were increasing, then that would mean that it would be decreasingly negative. The negative slope would be getting less steep as he moved to the right. Okay, everybody give me a 1 to 5 on that. Does that make sense? Okay, I mean, I know this kind of hurts your brain a little bit, but I want you to try to, and I purposely am trying to, I'm going to force you guys to do some of this in your head a little bit, because that's a skill. It's something that it takes a deep train of thought sometimes to build these models in your head, but the more you do it, the better you get. So once again, if the ant is walking on an uphill portion of the curve where there's a positive second derivative, then that means that the slope is going to be increasingly steep, right, as he walks to the right. If he's walking on a downhill portion, well, then that would, if the second derivative is positive, that would imply that the negative slope is getting less negative. It's getting more positive, which is equivalent to less negative, right? And so he'd see that slope kind of leveling off. And eventually, if the second derivative stayed positive, eventually that slope would presumably start to get positive and then more positive and more positive, right? Okay, so can you imagine then that if you had to think about that in terms of a descriptive word, how could we describe the function there? We could call that an upward concavity. The function would tend to be curling upward in regions where the second derivative is positive. Okay, now the opposite would happen if the second derivative were negative. If the second derivative were negative, then the rate of change of the slope would be negative. The value of the slope would be decreasing as the ant moved to the right. So positive slopes would get less positive, they would get less steep, and negative slopes would get more negative. If you contemplate that, doesn't that mean that it would have to have a downward curvature at that point? The function would tend to curl downward or have a downward concavity. Okay, so let's play with this a little bit, and I'm gonna put a link to all of these Desmos activities that I'm showing you. These are just, so I'll put a link to them, and then you guys can just go right to a Desmos webpage, and you can do the same stuff I'm doing if you want to mess with this a little bit later to kind of refresh your memories on this. So here's the first one. I got to remember what I did here. This is complicated. Let's see. So we've got this function. Let me turn everything off for a second. So here's our function. Okay, and as I move the value of a, all it's doing is it's dragging the ant along this function. Okay, a is just the input of our function here, right? In this case, no big deal. That's nothing new. Okay. As we're doing that, though, let's go ahead and let's graph I want you guys to look at two things here. So g of x is the derivative of the function, and h of x is the second derivative of the function. Okay, I want you to think here for a second. So this is giving us the value of a and the value of the second derivative. So you'll be able to see for any given value of a, you're going to be able to see this purple ordered pair up here is telling us the value of x and the value of the second derivative. Okay? And it's just going to hover above our point, the point that's actually on the function. Okay? At the same time, I'm going to show you a tangent to the curve. Okay, there's a tangent to the curve, right? So that's showing us the slope is pretty steeply negative here, right? Now look what happens if we start over here. Let's move over to this point. So at this point right here, you can see that, I guess I better move to where you can see, there we go, okay. So now you can see that the value of the second derivative is pretty large and negative, okay. What do you notice about? I want you to notice the relationship between the tangent line, the green tangent line, and the red function. That's f of x. Where does the tangent line sit relative to the red curve when the second derivative is negative compared to when it's positive? Now I'm going to very slowly move this thing along. Here, let me do this. I want this. Yeah, there we go. I'm going to very slowly move the value of a to the right. Oops, that's too fast. Let me slow this down a little bit. There we go. Okay. Look what's happening. The value of the second derivative is getting less negative, but it's still negative. Getting less negative, less negative. Look where that green tangent line is relative to the red function. The second derivative you can see is still negative, right? That's the y coordinate of that purple ordered pair is the value of the second derivative. Okay, look what's happening here. Okay, now it's switched. Now the second derivative is becoming positive. And it's getting more positive. Look what's happening to the relationship between the green tangent line and the red curve. What happened? Can anybody see a relationship there? Type it in chat. Did you see anything there interesting? Let me stretch out the x-axis just a little bit here. Let's try that. Let me drag this point back again. Watch this process again. I'll slow it down even a little bit more. Look where the green tangent is. Second derivative is negative. It's negative. It's negative. It's negative. Ooh, it's getting closer to zero. Still negative. Now it's positive. It went through zero and now it's positive. How does that change the relationship between the green tangent line and the red curve? You don't see this in textbooks a lot, but this is a really good visual test to see if a function is, if the second derivative is positive or negative. Do you notice that where the second derivative is positive? Well, first of all, the shape of the curve there is clearly concave up, isn't it? Bowl-shaped up. It's curved up. Over here where it was negative, it's curved down, right? So that's what we mean by concavity. Concavity, and you can kind of think of it in a two-dimensional rainstorm, a concave down function, right? So negative concavity tends to shed the two-dimensional water, and a concave up or positive concavity function tends to catch the water, right? Okay, but look at that tangent line. Do you notice that where the concavity is positive, the tangent line always sits below the curve? Where the concavity is negative, the tangent line sits on top of the curve. That's a really good test. It's just an immediate test, so you can always tell the concavity by just imagining a tangent to the curve, and that will always hold true. Okay? Everybody get that? Give me 1 to 5 on that. Does that make sense? Okay? And then at the point of transition, right here, where the second derivative, I don't know if I can get it just about, there, it's just right there, right? It's just barely, it's almost at zero. Well, look at that tangent right there. To the left, the tangent sits above the curve, and to the right, it sits below the curve, right? That's what that inflection point means. It's a point of transition in concavity, okay? All right, good. Okay, so there's one little demo, and like I say, I'll put just a little in the Google Classroom. I'll put a little Google Doc with links to these. It may already be there. If it's not, I'll do it today at lunch. Okay, here's another one. I gotta remember what this one does. Okay, this one's showing us. Okay, yeah, all this is doing is it's showing us 3 different curves. Here's the function, right? There's f of x, just a regular old parabola in this case. Okay. And we can bump this up if we want to a cubic in a second, but there's a parabola. G of x is going to be the first derivative. So what's the shape of the first derivative going to be if the function is parabolic? Everybody think about this. And everybody type your answer in chat for me. And there's no shame, and if you don't have it right, who cares? But we just got to have a discussion here, right? We want to talk about, so we're trying to look at the relationship between an upward concavity parabola, right? And that's just a parabola. And its derivative. So what's that going to do? Just type your answer in chat. What do you predict? Okay, I'm seeing lots of linear lines, and I want to know, is the slope of the line going to be positive or negative now? You're correct. It's going to be linear. Okay, good. Good. So you're making some important connections there. It's going to be positive. How come? Because the rate of change of the slope is positive on this thing, right? Everybody agree? It's going to be positive because the concavity of the function is positive. Okay? And so look what we get. If we graph that first derivative, there it is. Okay? Whoops, let's not do that. And if I drag this point along, you can see that the slope is increasing, right? And the value of the red function corresponds to the slope of the green function. As the green function gets steeper, the value of the red derivative function gets larger, right? Okay. What about the second derivative? The second derivative of our original function, f double prime, is going to be the first derivative of the derivative, right? So this is reinforcing a couple important things here. It's reinforcing the fact that the first derivative, f prime, is to f as f double prime is to f prime. They have parallel relationships, don't they? Right? So what is the shape of the second derivative function going to be now? Everybody type it in. What's the shape of the second derivative going to be? And that's what I'm going to graph next. Think about it for a second. Okay, good. Everybody agree? I'm getting a lot of similar answers. So it's going to be a horizontal line, and it's going to be positive valued, isn't it? Looks like in this case, it's going to be equal 1. It's going to be at 1, right? There it is. Okay. And we can see that the concavity, right, the second derivative gives us the output of the second derivative function gives us the concavity. In this case, just stays positive and constant. Okay, that makes sense. Okay, so now let's soup this up a little bit here. Let's bump this function up to where it's cubic. Okay, I'm gonna do two things. Let's do this first. Would everybody agree now that the concavity is downward, the rate of change of the slope is negative? And so now if I were to graph the first derivative of this downward opening parabola, doesn't it make sense that it's now going to be a line with a negative slope, right? And the second derivative function is just going to have a constant negative value, okay? Okay, so let's bump this thing. I'm going to do this. I'm going to make a positive again. And let's make this a cubic. Okay, so there's our, well, I can still do that. So there's our cubic function. What is the shape of the first derivative going to be? Type it in chat for me here. Think about the relationship now. The first derivative, the value of f prime is equal to the slope of green f, right? So it's going to be a parabola. Good. What's going to be the orientation of the parabola? Opening up or down? Okay. Up. Yeah, it makes sense, doesn't it? Because look, the slope of the curve is very positive there, right? So f prime is going to have a positive value. It gets down to its lowest value of 0, and then the slope starts to increase again, right? So there's the shape of the derivative function. And now we already did this drill, right? We know that the derivative of the red derivative, in other words, the second derivative then would have to be a line with a constant positive slope. Okay? All right. Okay, let's try another one here. Let's do this. Let's go. Okay, let's try that one. So what's the shape of the derivative function going to be? Aren't these kind of fun math puzzles? Don't you just love them? So what do you think? What's the shape of the derivative going to be? Okay, good. Parabola. And by negative parabola, I think what Ember's saying is it opens down, right? All you guys, when you say negative parabola, negative value of a. Okay, good. So now you're correct. That's correct. I want to know, is the vertex of that parabola going to sit above or below the x-axis? Okay, above. How come it's above? You're right, it's above. Defend your answer, though. Explain to me why. Ah, okay. I like Seth's answer. That's probably I would think that's the best way of looking at this, right? You know, we all know it's a downward opening parabola, don't we? Right? Because look, we can tell we have very extremely negative slopes to the left and extremely negative slopes to the right. So the value of the derivative function is going to be very negative and very negative, correct? Well, look, it has two horizontal tangents there and there. So if it's a downward opening parabola with two horizontal tangents correspond to x-intercepts, don't they, of the derivative function? Those are places where the derivative has a 0 value. And so this thing must have two solutions or two x-intercepts. So it's got to have a vertex above the x-axis then, doesn't it? The other way you could maybe think about that is, look, there's a little section between 0 and whatever that number is right there, where the slope of the function is actually positive, right? So the derivative function must peak out above the x-axis for a while because it has a positive derivative for a while, right? The function does. Okay, so does this make sense then? That's what the derivative looks like? Okay, doesn't that make sense? Because look, if I drag k along here, there's a place, whoops, let me turn this on too. Right, look, there's a place right there where we have a horizontal tangent of the green curve, which means we have a 0 of the red curve, right? And there's another place right there. Well, I can't quite get it, but you get the idea. I just got to nudge it a little bit to the right, and there's a horizontal tangent, so another 0 value of the derivative. Okay. And then if I look at the second derivative, well, that must be a line with a constant negative, with a negative slope. Everybody agree the second derivative has to be? Okay. So what is it? You notice a little trend here. I mean, this is just kind of a general theoretical conversation we're having, right? We're not doing any nuts and bolts calculus problems right now. We're just talking about some general relationships, but these are important relationships. What happens when you take successive derivatives of a polynomial function? Look, we started with a cubic here. And what happened every time we took a derivative? What happened to that polynomial? Okay, good. It's power decrease. So we could say that the degree of the polynomial gets reduced by 1 every time we differentiate, right? Okay, good. Let's maybe just play with this one last time. What if we do, I'm going to bump this thing up to, how about something like that? How about something like that right there? Okay, what kind of function is that? You can probably see the parameters on the left, so you can cheat, but what degree of polynomial? Talk to me about the degree of that polynomial. Think back to algebra 2. Okay, it's got to be at least fourth, doesn't it? Right? How do we know that it's an even polynomial? And I'll go ahead and zoom way out for a second, right? Okay, everybody agree we know it's an even polynomial? Because the end behavior is the same on both ends. Remember this from algebra 2? Even polynomials have similar end behavior. Odd polynomials have opposite end behavior, right? Okay, we know it can't be quadratic because it looks goofy. It's got some extra turning points in there, right? And then remember from algebra 2, we know that this has 1, 2, 3 turning points, doesn't it? 3 extrema, right? So we know if it has 3 turning points, then the degree of the polynomial has to be at least 1 bigger than the number of turning points, right? Think about that. A parabola has 1 turning point, and so the degree of the polynomial has to be 1 plus 2. It's a quadratic, right? That makes sense? Okay. So then if I take, just tell me generally speaking, this looks like it's a 4th degree polynomial. So what's going to happen when I take a derivative of this thing? We're going to get a cubic, aren't we? Right? It's going to be 3rd degree. Okay, how many turning points, meaning extrema, that's our kind of our algebra 2 term for an extrema, right? How many extrema is that cubic polynomial going to have? Okay. Good. It's 2, isn't it? Right? Because look, we know that it's going to have, look at the horizontal tangents. There's a horizontal tangent. There's a horizontal tangent. There's a horizontal tangent. So if this cubic has 3 x-intercepts, then it's got to turn twice, doesn't it? Right? There it is. Okay. And then if I were to graph the second derivative, we can see that this one's got 2 x-intercepts, right? And so it's going to have a vertex that sits below the x-axis. There it is. Okay, give me a 1 to 5 on that. Is that are you making some connections there? Okay? All right. Okay, so just quick summary here. So we know that when second derivative is greater than 0, that's upward concavity. A tangent to the curve sits below the curve. When the second derivative is negative, that's downward concavity, and a tangent to the curve would sit on top of the curve. Okay? All right, so then points of inflection, right? Those are going to be points of transition in concavity. Okay, and I guess if we go back, maybe I should go back to that for just a second. If I go back to like this guy. Okay, are there any points of inflection for this curve? There are not, are there, right? This one is, would everybody agree that this one is concave up? It's got a positive concavity everywhere, right? And if we graph the first derivative and the second derivative, yeah, we can see the second derivative here is always positive valued. It never changes sign, okay? How about now? Whoops. Does that have any points of inflection? Yes or no? Remember, points of inflection are transitions in concavity, just like extrema are transitions in slope, right? Isn't that true? A maximum is just a place where a function is transitioning from positive to negative first derivative, for positive to negative slope, for example, right? So a point of inflection is a place where a function transitions from positive to negative concavity, or vice versa. Okay? So this is going to have a point of inflection. The other way we can see that is clearly if I were to drag a tangent line along that curve, it's going to make a transition. The tangent line is going to start off sitting on top of the curve and end up sitting below the curve. So just estimate for me, you guys. What's the roughly the x value, would you say, where we make this transition here in concavity? Yeah, it seems good to me, like negative 0.3-ish. Does that look about right? Someplace kind of right in there, we're transitioning from being concave down, bowl-shaped down to bowl-shaped up. We can tell for sure if I look at the first derivative function. Now it's easy to tell, isn't it? Where is the point of concavity relative to the red graph? Where are we making a transition here in concavity? That's f prime. The red graph is f prime. Yeah, it's the vertex, isn't it? Everybody see that? It's going to be at the vertex. To the left of the vertex, you can see that the rate of change of the slope is negative, isn't it? Right? Isn't the slope of the red graph the rate of change of the slope of the green graph, right? And then at that vertex, it's going to transition from the rate of change of the slope transitions from 0 to positive because now the red derivative function has a positive slope, right? There's the second derivative. Its 0 corresponds with I'll prove it to you, corresponds with the 0 or the horizontal tangent of the red graph. Everybody get that? Okay, which is the transitioning concavity. Okay? All right, so what about these points of inflection then? Points of inflection are transitions in concavity. Okay? So you might be asking yourself, okay, there were two different kinds, points of inflection or inflection points or transition in concavity, just like extrema were transitions in slope, right? Positive to negative and negative to positive, right? Okay, now remember when we had transitions in slope, there were two different varieties. We had sharp corners, right? We could have peaks that were sharp peaks and valleys that were sharp valleys, or we could have smooth peaks and valleys, depending on whether the first derivative was undefined or equal to 0. Okay, so what does that mean in terms of points of inflection then? So is that a point of inflection right there? Yeah, that pretty clearly is a point of inflection, isn't it? Everybody agree? Okay. What about that one? Is that a point of inflection right there? I mean, clearly the concavity is going from negative concavity to positive concavity at that point, isn't it? So at first blush, it seems like it should be, but I'm going to claim, well, I'm not going to claim, I'm going to tell you that it's not a point of inflection. How come? Say it again, Seth. There's going to be a break in the first derivative. Yeah, now, if we go back to our discussion of first derivative, right? Remember, we made a very important statement. We said that differentiability implies continuity, right? A function must be continuous to be differentiable. Agreed? Okay. So what about here then? We should expect the same relationship to hold for a second derivative, right? The first derivative must be continuous for the second derivative to be defined. Okay? Well, not only is the first derivative not continuous, it's not even defined there, right? I mean, clearly we couldn't take a derivative of a function where the function's undefined. Everybody agree? If there's a hole or an asymptote or a break in the function or something, see what I'm saying? Then we clearly could not take the derivative of that function even to begin with, right? Well, we also, in parallel, we should not be able to take the second derivative of a function where the first derivative isn't even defined for us to differentiate, right? So what's the problem here then? Just glancing at this curve, how come we've got a problem there? Why can't we take a second derivative there at that point? And you're right, Seth, because there's going to be a break in the first derivative if I graph it. But even simpler than that, what can you tell me about the first derivative at that point right there? Does it exist? How come? Everybody type it in chat. Why does the first derivative not exist at that point right there? Everybody type that in chat. Give it your best shot. If you really don't know, just give me a question mark. That's okay. Okay. Sharp corner. There we go, right? Sharp corner. Where do derivatives not exist? They don't exist at sharp corners, at vertical tangents, or at places where we have any other place where the limit wouldn't exist, right? But the big ones were sharp corners, vertical tangents, or asymptotes, right? Those are the three that we really focused on when we were talking about derivative functions. So yeah, any place where the derivative is undefined, I can't take a second derivative. And so no, that is not an inflection point. Okay. So then how could we come up with a simple definition of an inflection point? So we know an inflection point is it's a transition in concavity, but what else must be true there? Is there you can tell I'm a big fan of these really simple visual tests, and they pay dividends later on. How can we look at this one and say, okay, that's clearly an inflection point, and this one is not, right? And think about our little tangent line trick that we had, right? We know that a function has positive concavity where the tangent line sits below the curve and negative concavity where the tangent line sits above the curve. And an inflection point must be a transition between the two, right? Well, that clearly applies for the blue one, but not the red one, right? So what could our definition of an inflection point be? It's a transition in concavity where what exists? Where the function's defined, okay, well, the function is defined there, right? Okay, true, where the derivative is defined, okay, good. But how could we make it even simpler? I want to make it visual. You got to think about that one too much, right? Okay, so what does that tell you about a tangent line then? Is there a tangent to the red curve at that point? There's not, right? Think about the definition of a tangent. A tangent is a line that intersects the curve at exactly one place that shares the slope with the curve, right? If I zoom in infinitely far, the tangent line should become the curve. Well, that would happen up here, wouldn't it? If I zoomed in on this, if I zoomed in on this function, on that tangent, right? Eventually that tangent line right there, if I zoom in, looks exactly like the curve, but there is no tangent there, right? Because there's no single tangent line that's going to match the behavior on the left and the right. So a really good, simple definition of an inflection point, and make sure you have this in your notes, or like you save these, because this isn't always in textbooks, but I think this is a really good definition. An inflection point is a point where the graph of a function has a tangent line and where the concavity changes. That is, in my mind, the very best definition of an inflection point. Okay, so we're getting to a point now where maybe we could start to we have maybe a little better feel for what an inflection point is, what concavity is. Now let's put this stuff to work a little bit. Let's just do a little practice. So sketch a graph of a function f that's continuous on the closed interval from a to b, such that f prime, and f double prime have the signs indicated in this little table down here, right? So I want you to match these things up here now. Which one of these, the first, second, third, or fourth, matches up with case A? What's the graph for case A? Okay, so it's telling us here that the function is f is positive, f prime is negative, and f double prime is negative on the interval from A to B. So every place on that interval, the signs of those first, the function, f prime, and f double prime are as given in column A. So let's take a vote. I'll tell you what we'll do here. You can vote anonymously. I'll make a poll on these things. How's that? This would be a good way to do it. Go ahead and vote. What do you think? Graph 1, 2, 3, or 4 from left to right. Which one corresponds to case A? Positive valued function, negative valued first derivative, negative valued second derivative. So I got to get, this is totally anonymous here. I got to get votes from everybody. So I should see 16 votes total on this. You got to think about it for a second. That's all right. Looks like an overwhelming majority here is leaning towards graph 4. Yeah, that makes sense, doesn't it? Positive valued means the graph is above the x-axis. F prime is negative means it's monotonic decreasing is how we would say that in math, meaning it's always decreasing. The ant's always walking downhill. And second derivative being negative valued means it's concave down. So tangents should sit on top of the curve, right? So clearly that's case 4, isn't it? Okay, let's try another one. What about B? Oops. Here, I'll give you a pull. So for case B, F is negative, F prime is positive, F double prime is positive. One, two, three, or 4, starting at the left. Okay, this one's a little more evenly mixed here. Well, let's see what we get. Let's try this. How about if we cross some out here? Okay, so case B, first of all, this is case B, isn't it? Right? So case B looks like right there. Okay? Can we cross any of these guys out? Well, F is negative, right, on the interval from 8. So it's got to be below the x-axis. So that guy right there gets crossed off, doesn't it? Okay. The first derivative is positive. So it's increasing. Okay, so that crosses off that guy, right? Everybody agree? And then finally, the second derivative is positive, which means it's concave up, which crosses out that guy. So our answer should be 4. Okay, make sense? All right, so we'll leave it there for now. The assignment, I'll make the assignment available. The first part of the assignment is just a lot of graphing stuff like this, and the second part is stuff that we didn't even get to. So you could start on it, but you're not going to be able to get super far. But do some of it for sure, so you can kind of reinforce what we did today so it doesn't go away. All right? Deal? All right, I'm here after school if you need me. Have a great day. Go out and play in the snow a little bit while you can, and I will see you on Thursday.